Faraday's law of induction is a basic law of electromagnetism predicting how a magnetic field will interact with an electric circuit to produce an electromotive force, a phenomenon called electromagnetic induction. It is the fundamental operating principle of transformers, inductors, and many types of electrical motors, generators and solenoids. The Maxwell-Faraday equation is a generalization of Faraday's law, and forms one of Maxwell's equations. History. Electromagnetic induction was discovered independently by Michael Faraday in 1831 and Joseph Henry in 1832. Faraday was the first to publish the results of his experiments. In Faraday's first experimental demonstration of electromagnetic induction, he wrapped two wires around opposite sides of an iron ring or torus. Based on his assessment of recently discovered properties of electromagnets, he expected that when current started to flow in one wire, a sort of wave would travel through the ring and cause some electrical effect on the opposite side. He plugged one wire into a galvanometer, and watched it as he connected the other wire to a battery. Indeed, he saw a transient current when he connected the wire to the battery, and another when he disconnected it. This induction was due to the change in magnetic flux that occurred when the battery was connected and disconnected. Within 2 months, Faraday had found several other manifestations of electromagnetic induction. For example, he saw transient currents when he quickly slid a bar magnet in and out of a coil of wires. And he generated a steady current by rotating a copper disc near the bar magnet with a sliding electrical lead. Michael Faraday explained electromagnetic induction using a concept he called lines of force. However, scientists at the time widely rejected his theoretical ideas, mainly because they were not formulated mathematically. An exception was James Clerk Maxwell, who used Faraday's ideas as the basis of his quantitative electromagnetic theory. In Maxwell's papers, the time-varying aspect of electromagnetic induction is expressed as a differential equation which Oliver Heaviside referred to as Faraday's law, even though it is different from the original version of Faraday's law, and does not describe motional EMF. Heaviside's version is the form recognized today in the group of equations known as Maxwell's equations. Lenz's law, formulated by Heinrich Lenz in 1834, describes flux through the circuit, and gives the direction of the induced EMF and current resulting from electromagnetic induction. Faraday's law. Qualitative statement. The most widespread version of Faraday's law states, the induced electromotive force in any closed circuit is equal to the negative of the time-rated change of the magnetic flux enclosed by the circuit. This version of Faraday's law strictly holds only when the closed circuit is a loop of infinitely thin wire, and is invalid in other circumstances as discussed below. A different version, the Maxwell-Faraday equation, is valid in all circumstances. Quantitative. Faraday's law of induction makes use of the magnetic flux phi-b through a hypothetical surface sigma whose boundary is a wire loop. Since the wire loop may be moving, we write sigma for the surface. The magnetic flux is defined by a surface integral, where d is an element of surface area of the moving surface, sigma b is the magnetic field, and b d is a vector dot product. In more visual terms, the magnetic flux through the wire loop is proportional to the number of magnetic flux lines that pass through the loop. When the flux changes, because B changes, or because the wire loop is moved or deformed, or both, Faraday's law of induction says that the wire loop acquires an EMF, defined as the energy available from a unit charge that has traveled once around the wire loop. Equivalently, it is the voltage that would be measured by cutting the wire to create an open circuit, and attaching a voltmeter to the leads. Faraday's law states that the EMF is also given by the rate of change of the magnetic flux, whereas the electromotive force and phi-b is the magnetic flux. The direction of the electromotive force is given by Lenz's law. For a tightly wound coil of wire, composed of n identical turns, each with the same phi b, Faraday's law of induction states that where n is the number of turns of wire and phi b is the magnetic flux through a single loop, Maxwell-Faraday equation. The Maxwell-Faraday equation is a generalization of Faraday's law that states that a time-varying magnetic field is always accompanied by a spatially varying, non-conservative electric field, and vice versa. The Maxwell-Faraday equation is where is the curl operator, and again E is the electric field and B is the magnetic field. These fields can generally be functions of position r and time t. The Maxwell-Faraday equation is one of the four Maxwell's equations, and therefore plays a fundamental role in the theory of classical electromagnetism. It can also be written in an integral form by the Kelvin-Stokes theorem, where, as indicated in the figure, sigma is a surface bounded by the closed contour sigma, E is the electric field, B is the magnetic field, D is an infinitesimal vector element of the contour sigma, Da is an infinitesimal vector element of surface sigma. If its direction is orthogonal to that surface patch, the magnitude is the area of an infinitesimal patch of surface. Both D and Da have a sign ambiguity. To get the correct sign, the right-hand rule is used, as explained in the article Kelvin-Stokes theorem. For a planar surface sigma, a positive path element D of curve sigma is defined by the right-hand rule as one that points with the fingers of the right hand when the thumb points in the direction of the normal end to the surface sigma. The integral around sigma is called a path integral, line integral. Notice that a non-zero path integral for E is different from the behavior of the electric field generated by charges. See gradient theorem. The integral equation is true for any path sigma through space, and any surface sigma for which that path is a boundary. If the path sigma is not changing in time, the equation can be rewritten. The surface integral at the right-hand side is the explicit expression for the magnetic flux phi b through sigma. Proof of Faraday's law. The four Maxwell's equations, along with the Lorentz force law, are a sufficient foundation to derive everything in classical electromagnetism. Therefore, it is possible to prove Faraday's law starting with these equations. Click Show in the box below for an outline of this proof. Counterexamples to Faraday's law. Faraday's disk electric generator. The disk rotates with angular rate omega, sweeping the conducting radius circularly in the static magnetic field B. The magnetic Lorentz force V times B drives the current along the conducting radius to the conducting rim, and from there the circuit completes through the lower brush and the axle supporting the disk. This device generates an EMF and a current. Although the shape of the circuit is constant and thus the flux through the circuit does not change with time. A counterexample to Faraday's law when over broadly interpreted. A wire connects to two touching metal plates to form a circuit. The whole system sits in a uniform magnetic field, normal to the page. If the word circuit is interpreted as primary path of current flow, then the magnetic flux through the circuit changes dramatically as the plates are rotated, yet the EMF is almost zero, which contradicts Faraday's law. After Feynman Lectures on Physics Volume 2 page 17-3. Although Faraday's law is always true for loops of thin wire, it can give the wrong result if naively extrapolated to other contexts. One example is the Homopolar Generator. A spinning circular metal disk in a homogeneous magnetic field generates a DC EMF. In Faraday's law, EMF is the time derivative of flux. So a DC EMF is only possible if the magnetic flux is getting uniformly larger and larger perpetually. But in the generator, the magnetic field is constant and the disk stays in the same position, so no magnetic fluxes are growing larger and larger. So this example cannot be analyzed directly with Faraday's law. Another example, due to Feynman, has a dramatic change in flux through a circuit, even though the EMF is arbitrarily small. See figure and caption above right. In both these examples, the changes in the current path are different from the motion of the material making up the circuit. The electrons in a material tend to follow the motion of the atoms that make up the material, due to scattering in the bulk and work function confinement at the edges. Therefore, motional EMF is generated when a material's atoms are moving through a magnetic field, dragging the electrons with them, thus subjecting the electrons to the Lorentz force. In the homopolar generator, the material's atoms are moving, even though the overall geometry of the circuit is staying the same. In the second example, the material's atoms are almost stationary, even though the overall geometry of the circuit is changing dramatically. On the other hand, Faraday's law always holds for thin wires, because there the geometry of the circuit always changes in a direct relationship to the motion of the material's atoms. Although Faraday's law does not apply to all situations, the Maxwell-Faraday equation and Lorentz force law are always correct and can always be used directly. Both of the above examples can be correctly worked by choosing the appropriate path of integration for Faraday's law. Outside of context of thin wires, the path must never be chosen to go through the conductor in the shortest direct path. This is explained in detail in The Electromagnetic of Fluid by W. F. Hughes and F. J. Young, John Wiley Inc., Faraday's Law and Relativity. Two phenomena. Some physicists have remarked that Faraday's law is a single equation describing two different phenomena: the motional EMF generated by a magnetic force on a moving wire, and the transformer EMF generated by an electric force due to a changing magnetic field. James Clerk Maxwell drew attention to this fact in his 1861 paper on physical lines of force. In the latter half of Part 2 of that paper, Maxwell gives a separate physical explanation for each of the two phenomena. A reference to these two aspects of electromagnetic induction is made in some modern textbooks. As Richard Feynman states, so the flux rule, that the EMF in a circuit is equal to the rate of change of the magnetic flux through the circuit, applies whether the flux changes, because the field changes, or because the circuit moves. Yet in our explanation of the rule we have used two completely distinct laws for the two cases, for circuit moves and for field changes. We know of no other place in physics where such a simple and accurate general principle requires for its real understanding and analysis in terms of two different phenomena. Richard P. Feynman. The Feynman Lectures on Physics. Einstein's view. Reflection on this apparent dichotomy was one of the principal paths that led Einstein to develop special relativity. It is known that Maxwell's electrodynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. The observable phenomenon here depends only on the relative motion of the conductor and the magnet, whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. For if the magnet is in motion and the conductor at rest, there arises in the neighborhood of the magnet an electric field with a certain definite energy, producing a current at the places where parts of the conductor are situated. But if the magnet is stationary and the conductor in motion, no electric field arises in the neighborhood of the magnet. In the conductor, however, we find an electromotive force, to which in itself there is no corresponding energy, but which gives rise, assuming equality of relative motion in the two cases discussed, to electric currents of the same path and intensity as those produced by the electric forces in the former case. Examples of this sort, together with unsuccessful attempts to discover any motion of the Earth relative to the light medium, suggest that the phenomena of electrodynamics, as well as of mechanics, possess no properties corresponding to the idea of absolute rest.